Okay. Hello, everyone. I'm pleased to introduce Song Mei, who's a PhD student here at ICME at Stanford, and he's going to talk about mean field theory and tangent kernel theory of neural networks, which perfectly connects us to the previous speaker, who was Jeffrey Pennington, and perfectly connects us to the next speaker, who's Arthur Jacob. Just I want to remind you that we had an announcement that students have to ask questions during lecture on Canvas, and part of your grade will be asking those questions. So you just post a question, and we will pick the best questions at the end of the lecture based on our, and just ask some of these questions. Thank you for your participation.
Can we also ask questions during the lecture or not?
Yes. But yes. Yes. Not too many.
Okay.
No, I'm just kidding. You ask anything. But part of the grade is asking questions. Okay.
Great. Thanks for the invitation. I'm Song Mei. I'm a 6-year PhD student at Stanford in ICME. This talk is about mean field theory and tangent kernel theory for neural networks. I guess everyone at Stanford perhaps took some classes or worked on some projects related to applications of deep neural networks. Deep learning has been applied to many scenarios, including computer vision, generative modeling, and reinforcement learning. Their real-life applications are autonomous vehicles, WaveNet for generating speech, and playing games. Although deep learning is very successful in terms of application, its mathematical foundations is still not well established. The challenges of mathematical challenges of deep learning are mostly twofold. The first is about its optimization. The training loss of deep neural network is a highly non-convex objective function, and local search algorithm usually could potentially find a bad optimizer. But why in practice stochastic gradient descent algorithm find near global minimizer of neural networks? And second challenge is about its generalization. Usually the number of parameters in a deep neural network is more than the number of data in the training process. So statistical theory will suggest that when you have more parameters than data, you will overfit the data, and the generalization error will be huge. But in practice, neural network can fully fit the data and also generalize well. So we would like to understand these two challenges of deep neural networks today using the mean field theory and the tangent kernel theory. These are two theories that emerged just last year and has been the focus of research in the recent 2 years. First, I will introduce the mean field theory for neural networks, and I will use these 2 layers neural networks as an example. So for 2 layers neural networks, there are actually 3 layers: the input layer, the hidden layer, and the output layer. The input layer is a layer of your feature X, which are images, perhaps, and the output layers are their labels. Between the input layer and the hidden layer, the weights, we denote it as WIs. Between the hidden layer and output layer, the weights, we call it AIs. In terms of mathematics, we have parameter theta from theta 1 to theta capital N. Capital N is the number of neurons in the hidden layer. Each parameter theta I is a d-dimensional vector. The prediction function of 2 layers neural network is simply the average of the sigma star function associated with each parameter theta I. Theta I is a concatenation of AI and WI. So this is equivalently the average of AI times an activation function of the inner product of Wi and x. The activation function can be taken whatever you want, for example, ReLU or sigmoid. Then we can define the risk function associated to n neurons. And the risk function is simply defined as the expectation taken with respect to data of the loss function between the label y and the architecture of two layers network. We consider the dynamics of two layers network, which is the gradient flow of the risk function Rn. Gradient flow means continuous time gradient descent. And the time derivative of the parameter theta I is just goes to the direction of negative gradient of the loss function. And here these are scalar parameter serves for step size. So the difficulty of this analyzing two layers network is that it's a highly non-convex objective function, and there could potentially be many local minimizers. One way to analyze it is through landscape analysis. That means to try to explain, because the landscape of this objective function is very nice. All the local minimizers are close to global minimizers, so we can find good local minimizer using local search algorithm. But this line of work is not very successful. So most of these citations are before 2018, and within these works, people analyzed the landscape of neural networks, but they made some strong assumptions so that they have nice results. For example, in these two papers, they analyze linear neural network. That means the activation function is a linear function. And in this case, they show that there's no spurious local minimizer. But in practice, people will never use activation functions which are linear. In the second work, they show that quadratic two layers network has no spurious local minimizer. Quadratic means the activation function is quadratic, but in practice, no one will use that. And all these papers establish strong results upon the landscape, but also with strong assumptions that are not realistic in practice. So to last year, people find the landscape analysis is frustrating, and people want to find some other perspective to explain two layers or multi-layers neural networks. And here comes the mean field perspective.
If your activations are linear, why isn't the problem just convex?
Because it's convex. Okay, it's not convex, because it's linear in the product of random matrices right? So it's convex with respect to product of two matrices, but it's not convex with respect to each individual. It's not convex with to, yeah, it depends on the parameterization. Here comes the mean field perspective of analyzing two layers networks. So the observation is the following. If you look at the prediction function, and this is the average of the neuron associated to each parameter theta I, you can rewrite it as the integration of the sigma star function with respect to rho hat. Rho hat here is empirical distribution of the weights. So rho hat is a distribution in the d-dimensional Euclidean space. Using this reformulation, we can rewrite the risk function as a functional of a distribution in the d-dimensional Euclidean, in the space of distribution on d-dimensional Euclidean space. And the functional is defined simply resemble what we had for this risk function. Okay, so that means the effective parameter in two layers network is this empirical distribution. And this motivates us to consider equivalent characterization of the dynamics using this empirical distribution. So that means if you consider the continuous time gradient flow on the parameter theta I from 1 to capital N, we regard this parameter theta I as particles, so I will call them particles. The particles will just go to the direction of negative gradient of the risk function. at initialization, we take it to be theta I 0. And we can also consider another dynamics, which is a dynamics on the space of distribution. And this is a partial differential equation. In the left-hand side of this equation, this is a time derivative of this distribution. And on the right-hand side of this equation, this encodes the spatial information of distribution at time t. And initialization is taken at the empirical distribution at time 0 of these particles. Okay? So now I define two dynamics. One dynamics is on the particles, another dynamics is on the distribution. And their connection is just through their initialization. The claim is the following. If we look at the solution of this partial differential equation at time t, this gives you a distribution, and this distribution is exactly the same as the empirical distribution of the particles at time t. So this gives you a new perspective on the dynamics of two-layer networks. So the gradient flow dynamics is upon the particles. Each particle goes to the direction of negative gradient of the risk function. And here we have particles in blue, and after a small amount of time, they move and change to the particle in red. Okay, but we can.
In which space are we looking at these particles?
These particles, they are theta i's. They are theta i's. So.
Theta i's are the weights, or like?
Are the weights.
And so, in which space are we looking at this? Like this picture, this schematic, in which space is it? Like, what are the axes?
Okay, so each particle is a theta I. So this is a d-dimensional Euclidean space. You can project it onto 2D and plot this stuff. And if the number of particles is very large, then you can think of them as point clouds, and you can talk about the density of these point clouds. So if you look at the density of the point cloud at initialization, this gives the blue curve, and after a small amount of time, the density change to the red curve, and the change of this density will evolve according to this partial differential equation. So this gives you a dynamics on the distribution. And the proof of this claim is very short. You just use a test function to hit this partial differential equation using some chain rule and integration by part. You get these results. So now, so here we take this theta I to be the concatenation of AI and WI. Which one?
Yeah, just that one.
So here we just use a test function f and look at the time derivative of f hit by the distribution, and these are all equalities and given by chain rule and integration by part. Okay, so these are totally exact. What is this partial differential equation? In terms of physics, this is called the nonlinear transport equation that describes the motions of particles with pairwise interactions. So in physics, this is called the mean field approach, modeling the interacting particle systems. In terms of mathematics, this is the gradient flow of the risk function of R, but this is not the gradient flow in the Euclidean space. This is a gradient flow in the distribution space with Wasserstein 2 metric. So using this gradient flow point of view, we can see that this partial differential equation is effectively optimizing this risk function of R. So now we derive a sequence of partial differential equations indexed by the number of neuron n. So the question is, what if we let the number of neurons goes to infinity? We have a sequence of PDE, and their initialization condition is the empirical distribution of the particles at time 0. And suppose we sample the theta I0 to be independently sampled from rho 0, which is a distribution in d-dimensional Euclidean space. Then we expect that as the number of particles goes to infinity, this empirical distribution at time 0 will converge in some sense to this rho 0. And then you would expect that the limiting dynamics will also converge. That means this rho n at time t will converge to the limiting distribution rho t. And rho t satisfies this PD with initialization condition rho 0. And this, we show that indeed this is the case. Okay? So under some assumptions, we can show that if we sample this particle at time 0 independently from rho 0, we denote rho nt to be the solution of the gradient flow, and rho t to be the solution of PDE. Then their difference is bounded by using a test function f to measure the distance between these two distributions. Then the distance is bounded by a small term, where this term blows up as t goes to infinity. But if you take the time horizon to be of constant order, to be of order 1, then this term will converge to 0 as the number of particles goes to infinity. And this result immediately gives us interesting implication, which means that as number of neurons goes to infinity, we have a fixed limit. We have a fixed scaling limit. That means the convergence speed of n neuron gradient flow is actually independent of the number of particles, as the number of particles is very large. That means we reduce the effective dimension from effective dimension of an optimization problem in dimension n times d to dimension d. Okay, so here is, if you don't trust the theory, here is a figure that illustrates this convergence when the number of particles is huge. So we implement the gradient flow using stochastic gradient descent algorithm, and then we solve the partial differential equation. Here we plot the profile of the weights at different times at different steps. So here are 3 different number of iterations, and you can see that the solution of the partial differential equation coincides with the profile of the histogram of solution of SGD.
So this is like the distribution of the weights.
Yeah,
and predicted.
The distribution of the weights projected onto 1 dimension.
How do you solve the PDE?
To solve this, so this is a special example where the dimension is huge, but it's spherically symmetric. So we can reduce the PD into 1 dimension and solve the 1-dimensional PD. But for the SGD, we run it in high dimension.
So a more interesting function instead of the projecting with 1 dimension
Mm-hmm.
would be something like misclassification. Is that a proper function instead of that?
I mean, you can put any projection. I mean, this is just one way to illustrate this SGD PD relationship. You can put any favorite function you want. In the next figure, we put the function to be just a risk function.
Okay.
Right? So I think this is what you want. So you want to monitor the risk function along the trajectory. So here we solve the PDE, and the solution is in these solid lines. And here are 2 solutions. In one solution, we can see that the risk function converges to 0 as time goes to infinity. And using another initialization, we are solving the same PDE, but with 2 different initializations. Then in another case, we can see that the solution of PDE will stack at some perhaps bad local minimizer. But then if you run the stochastic gradient descent algorithm, then it will track this solution of PDE. if the PDE converges to zero risk, then the solution of SGD will converge. If the PDE doesn't converge to zero risk, then the solution of SGD will also stack as some bad local minimizer.
Do you saw here a low dimension PDE as well?
Yes. Okay, so using this PDE point of view, the question is, what are the benefits? So one natural question is, can we show that the PDE will converge to the minimizer of the risk functional as the time goes to infinity? And in general, the answer is no. We have example. In this case, we can show that this PDE, okay, this is numerically, but we can show that it's numerically is stacked as some bad local minimizer. So in general, it will not converge. But in our paper, we show that sometimes, yes, we can show that in some case, if we consider some special distribution of data, then we can show the PDE converge to zero risk minimizer. And we have some general result for the convergence of this PDE if we insert additional noise in the SGD. So that means if we consider this noisy gradient flow, we add additional noise. There are Brownian motions. We add Brownian motion into the gradient flow. Then we can show that the corresponding PDE, we just modify it. We just add a diffusion term here. And this modified partial differential equation can be interpreted as the gradient flow, the Wasserstein gradient flow of free energy, where the free energy has an energy term, which is original risk functional. And there is this entropy term, which is strongly convex in the parameter in the distribution rho. So it's strongly convex in the Euclidean sense, but one can show that this free energy has a unique fixed point, has a unique stationary point. So that means gradient flow will converge to the minimizer of this free energy. So we have a theorem shows that if we solve this partial differential equation, that time goes to infinity, it will converge to the minimizer of the free energy. And using this partial differential equation as an interpolation, we can show that if we run SGD algorithm with a large number of neurons and with a sufficiently small step size, then the risk function will converge to approximate global minimizer of the risk function. One caveat is that this theorem is not so quantitative in the sense that the convergence rate is not polynomial in the number of, it's not polynomial in dimension and data. So it's a convergence result, but it's not so quantitative. And this mean field perspective emerged last year, and till now there are many extensions of this work. So I guess the most interesting topic is to extend this mean field formulation to multi-layers neural networks. And there are 3 papers talking about this. And it's exciting that we can extend it to multi-layers, but there are certain limitations of this theorem. And the study of this mean field theory is still ongoing topic. So next we move to the tangent kernel theory, which is also a theory that emerged last year and explained the success of optimization of neural networks. But it gives us another perspective. Okay. So let's consider a prediction function f of x and theta. And let's say this prediction function f is a multi-layer neural network. The specific formulation of this f is not very important. And what we will do is to linearize this function f around a random parameter theta 0. The linearization means we do Taylor expansion. So there is the zero order term, the linearization term, and the higher order term. It turns out that if F is a multi-layer neural network, then with proper initialization, then the zero order term and the higher order term, they are not very important. Okay? So the only term important in training neural network is this linearization term. And this motivates us to define neural tangent model, which is a model which is a linearization of this function f. Okay, so this fnt is another function. It's a linear function in theta, and it's related to this original neural network f, but it's a different model. The way to think about this gradient respect to theta of f at x and theta 0, the way to think about this object is to regard it as a feature map. So it maps the original feature x to a high-dimensional space, and you fit a linear function of this feature in this neural tangent model. Okay, so this is essentially the interpretation of this neural tangent kernel. So if we regard this gradient with respect to theta of f as a feature map, then we can define a kernel which is the inner product of this feature map at x and y. And the neural tangent kernel, these papers just say that under certain conditions, where these conditions involves initialization and step size of the training of fully trained neural networks, then but these conditions are different from the condition of the mean field theory. And under these conditions, one can show that the trajectory of the gradient flow on the empirical risk of the neural tangent model and fully trained neural network is uniformly close. So that means if we train a neural network as the number of parameters is large with certain initialization, then you get zero training error. So some people believe that this fully explains the optimization, the success of neural network. So does these neural tangent models fully explain the success of neural networks? Is still an ongoing debate. So we would like to argue that this linearized model cannot fully explain the success of neural network in terms of their generalization. So empirically, the generalization of these neural tangent models are not as good as the fully trained neural networks. Here is the data from Stanford 10 experiments. So in the group by Sanjeev Arora, they look at they train the Stanford 10 using convolutional neural network. The best convolutional neural network gives a classification error which is as low as 5%. But if we use a linearized neural network, if we linearize a convolutional neural network and get a convolutional neural tangent model, then the classification error, the best classification error is 23%. And the corresponding convolutional neural network to this convolutional neural tangent model gives classification error 19%. So that means the linearization successfully explained the optimization, but in terms of generalization, it's not as good as fully trained neural networks. So we would like to explain the generalization separation between the linearized model and the fully trained neural networks. So let's go to something more specific. We still consider two layers neural network. So this is a summation of AI times activation function composite on the inner product of Wi and x. X is the input vector, which is d-dimensional in the d-dimensional Euclidean space. And the bottom layer weights are Wi's, and the top layer weights are AI's. We consider the linearization of this neural network around a random initialization. So After we do Taylor expansion, there is this the zero order term and the higher order term. These are not important. So what is important is the linearization term. And there are two terms in this linear term. And the first term corresponds to that if you fix the first layer with Wi and linearize over the second layer with. So this part, we associate this part with a function class, which is this function class f rfn. N is the number of neurons used in this neural tangent model. And in this function class, we fix the wi's and only optimize over these ai's. So because this function class is exactly the same as the random feature function class, so this RF index denotes the random feature. Okay. And then there is a more complicated term, and in this term, we linearize. We fix these ai's and linearize over the wi's, and we associate a function class with the second term, and this function class we call the tangent kernel, the neural tangent class, and in this function class there are still n neurons, and the function class and the functions in this function class is of this form. And the parameters it will fit in this function class is these ai's. These ai's are d-dimensional Euclidean vectors. These ai's are different from this ai. So this ai is a scalar, and this ai is a d-dimensional vector. So in a function class, in the neural tangent class with n neurons, because each parameter is a d-dimensional Euclidean vector. So the total number of parameters in this neural tangent class is n times d. And we will consider the approximation error of this function class to approximate a function in L2 space. And we define the approximation error, which is the infimum of a function in this function class with n neurons. And the infimum with respect to the function, and the quantity we minimize is the expectation between the expectation of the square loss between the ground truth function f star and the function in this function class. Okay. And the first result we show upon this approximation is the staircase lower bound. First, we consider the random feature class. We take the number of neuron n, capital N, and the dimension goes to infinity together. But we take the number of neuron goes to infinity faster. We take capital N as d to the L. And we take these wi's to be ID sampled uniformly from the d-dimensional sphere. Then if we consider the approximation error using this random feature function class with n neurons, this approximation error is lower bounded by the norm square of the projection of the ground truth function onto high degree polynomial. This p greater than L is a projection operator orthogonal to the space of degree L polynomials. So this result means that with n equals d to the k, if the number of parameters is d to the k, we can only fit a degree k polynomial. And we have similar result for the neural tangent model, where we assume the number of parameters we have the number of neurons we have is d to the L. It is also d to the L. And the approximation error using a function in the neural tangent class with n neuron is lower bounded by the norm square of the projection of the ground truth function onto high degree polynomial. And this p greater than L plus 1 is a projection operator orthogonal to the space of a polynomial of degree L plus 1. So that means we have d to the L neuron, but in this function class, we have d to the L plus 1 number of parameters. We can only fit a degree L plus 1 polynomial. So using a figure to illustrate these results, we have this staircase-shaped lower bound. Suppose we can decompose the ground truth function f onto orthogonal polynomials. Then the risk function, the approximation error, versus the number of parameters display this staircase shape. And here the x-axis is not the number of parameters itself, it's log the number of parameters over log d. Okay? So you can see that there is a drop of the approximation error when the log number of parameters over log d pass through an integer, pass through integers. So when the number of parameters is less than dimension, we can only fit a constant function. When the number of parameters is less than d squared, we can only fit a linear function. And when the number of parameters is less than d to the 3, we can only fit a quadratic function, so on and so forth. So this approximation lower bound imply a separation result between the approximation of the linearized neural network and the fully trained neural network. Suppose we look at, suppose we want to approximate a function on the d-dimensional sphere, which is a degree k polynomial of only the first coordinate. Okay, so this is a very simple function we would like to approximate. Then, using the neural tangent model, which is a linearization of this neural network, the number of neurons we would like to use is of order d to the k minus 1. But suppose we want to use a fully trained neural network to approximate this target function. We only need to use order 1 number of neurons. So the first claim is our staircase lower bound. And the second result is trivial because you just want to align the weights wi to the first canonical coordinate. Okay. So this shows a separation. In the literature, there are other theories that want to show a separation between the approximation of random feature, which is a linearized neural network, with the neural network itself. And these theories are based on the RKHS theory. So the difference of our new result with this theory is that the first difference is that here we assume the target function is in L2. It's just any general function. But in the typical RKHS theory, they need to assume the function is in the RKHS. And one knows that RKHS is much smaller than a function in L2. And the second difference of our result with classical theory is that we take this number of neurons and dimension goes to infinity together, but we take neuron to be d to the k. And in the classical theories, the dimension is fixed and the number of parameter goes to infinity. So these are the two differences of this new result with classical theories. And then we would like to show the second result, which is the double descent phenomena. This is a phenomena related to the generalization of neural network, and it was just formalized at the end of last year. So to explain this phenomena, first we would like to look at experiment. So we just want to do image classification, and the data set is MNIST. So this experiment is not done by us. It's done by a paper by the group of Nati Strabel, but I will explain what's their setup. Okay, so they project the image onto. They project the original image is 28 by 28, but they subsampling such that the image is in 100 dimension. And the labels are handwriting digits from 0 to 9. The training data size is 50,000, and the test data size is 10,000. And then people train this they train this MNIST data set using 2 layers fully connected neural networks. And this is the standard 2 layers networks. And they use cross entropy loss function. And they use stochastic gradient descent algorithm to train this loss function. And they find an approximate local minimizer and stop, and they report the training error and the test error. And here I didn't specify how to choose the number of neurons in the neural network. This is the model complexity of this neural network, and they will train this data set using different number of neuron n, and report the training error and the test error. And then they plot the risk function respect to this model complexity. And surprisingly, they found this surprising curve. So when the model complexity is very small, and you increase the model complexity, then you can see that, okay, perhaps we can see this figure is more clear. So the training error will decrease, and the test error will decay together with the training error. And the gap between the training error and the test error becomes larger and larger. So this is what people expected. This is the traditional regime. And the gap becomes larger and larger. It's because of the model complexity becomes larger and larger. So the variance becomes larger. But what is surprising is that when the training error approximately touch 0, there is a singularity of the test error. But then, if you increase the model complexity further, the test error will decay and will continue to decay, and it goes to a constant as the model complexity goes to infinity. And these experiments are not only done by a single group. These experiments and these experimental results are found within various groups. And here I just stole the experimental result from these 2 papers. Okay, so this phenomenon was just formalized last year by this paper by the group of Misha Belkin. They say that this is, they call it a double descent phenomenon. Where this phenomenon is surprising in the sense that traditionally in statistical learning theory, people will believe that the test error versus the model complexity will display a U-shaped curve. That means when the model complexity becomes larger and larger, the training error becomes smaller. But the training error becomes smaller because your bias, because the model complexity is larger, so the approximation error becomes smaller. The bias becomes smaller. The test error will decay at first and then goes up. It goes up because the variance blows up. But in the experiment of neural networks, people find this double descent phenomena in the sense that when the model complexity starts to grow at the beginning, it displays a U-shaped curve. But at an interpolation threshold, there is a singularity of the test error. But then, as you increase the model complexity again, you will find the test error will be monotonically decreasing in the over-parameterized regime. And finally, if you increase the model complexity and it goes to infinity, then you will find the global minimum of the test error appears in the highly over-parameterized regime. So these are the features of this double descent curve. So this paper just appeared on arXiv at the end of last year. And at the beginning of this year, 2 papers appeared on arXiv, tries to explain this double descent phenomena using the simple linear model. So they call it linear model with random covariates, and this is, they call it misspecified linear model, where the model is simply the ground truth function is a linear function of the covariate x, and you add ID Gaussian noise. And you use a linear model to fit this ground truth function, and report the training error and the test error. So in this figure, there's only the test error. So you find the singularity when the model complexity is the same as sample size. Okay. So here is a simple explanation of this surprising singularity. Let's consider the linear model, but we take this beta star to be 0. So the ground truth function, in the ground truth function, x and y, they are independent. We generate this xi by ID Gaussian features. And we generate this y as pure noise, pure Gaussian noise. Okay? Then if we compute the test error, then the test error will be proportional to expectation of beta hat 2 norm square. And this is expectation of the 2 norm square of x pseudo inverse y, which is proportional to expectation of trace of x transpose x pseudo inverse. If you know a little bit about the random matrix theory, then this X matrix is X transpose X is called the V-shard matrix, and the spectral property of this matrix is well studied. You will see that if the number of data is not equal to the dimension of the X, then X will be well conditioned. All the singular values of X will be away from 0. And then this trace of X transpose X pseudo inverse will be away from infinity. But when the sample size is approximately equal to the dimension, then this X becomes a square matrix, and the least singular value of this matrix X will almost touch 0. That means this matrix X will be infinitely yield conditioned. Then if you compute its X transpose X pseudo inverse and you compute its trace, it will blow up to infinity. So this is a simple mathematical interpretation of the singularity. And if we want to use just a sentence to describe this singularity, I come up with this sentence that the model has marginally enough parameters to interpolate all the data. So it interpolates the data in a very awkward way. To fit this noise, the coefficients beta hat 2 norm square need to blow up to fit this noise. Okay? So that means if we want to just interpret this singularity of this double descent curve, then you can see it already in the linear model, and you can explain it very easily. But then if you look at the generalization curve of the neural network, of fully trained neural network, and the generalization curve of the linear model, you will see that they are not exactly the same. You see there is a singularity at the interpolation threshold, but you don't see. But in the neural network, the generalization error above this interpolation threshold will be monotonically decreasing, and the global minimum will be found at the highly overparameterized regime. Whereas in the linear model, the generalization error after the interpolation threshold can decrease first and then increase. And the global minimum could appear in the underparameterized regime. So these are the features that linear model cannot explain that appeared in the fully trained neural networks. So our goal is to find a tractable model that exhibit all the features of the double descent phenomena. And we come up with a simple model, which is a random feature model. You can regard it as a linearized neural network. In this random feature model, okay, so this is a 2-layers network, but you fix the first layer with Wj. You take these weights to be independently sampled uniformly from the sphere, and then you fix them. You only train the coefficients Aj. So this is a 2-layers neural network with the first layer weights fixed and random. So the full description of the setting is the following. We consider the random features regression and minimize the training error with some regularization of the coefficients A. We penalize the 2 norm of A squared. And then we get the minimum of the training error. We get A hat lambda, and we measure the test error of this minimizer. And there are many notations in these two expressions. Let me parse these notations one by one. So xi's are our data. We assume they are uniformly sampled on the sphere. And the yi's are a function of xi, where f star, we make some assumptions on f star, but we basically assume f star is just a L2 function. And the variance of the noise, we assume it to be tau squared. And J's are the weights. We also assume it's uniformly sampled on the sphere. And this activation function, we make some assumption, but basically it includes almost every activation function, include ReLU and sigmoid. There are some technical assumptions on f star and the activation function, but they are not very strict. And here there are 3 important parameters. Little n is the number of data. Capital N is the number of features. So capital N is the number of is the dimension of the vector A. And D is the dimension of the feature. And we assume the asymptotic regime where the capital N over D goes to a constant per psi 1. And little n over D goes to a constant per psi 2. And we let all these 3 parameters goes to infinity together. So this is the setting of this random feature regression. So if we look at the test error in this setting, then our theorem gives asymptotic, the precise asymptotic of this test error, which involves this function B and function V. And these functions are analytically given in this formula. So this formula seems a little bit complicated, but actually it can be computed using a single PC in a millisecond. So basically, you solve a self-consistent equation. These are degree 4 polynomials. You find a root of a degree 4 polynomial and compute some polynomials, and you will get this function B and function V. And then you construct and you combine this B and V. This B is the bias term, the V is the variance term, and you get this asymptotics of the test error. So now we get these equations. We want to plot these equations and get some intuition for this generalization of the random features model. So, okay, we have similar results for the training error. And if we plot the training error and the test error together, we plot under 2 conditions, under 2 cases. In the first case, we take the regularization parameter lambda to be 0. And in the other case, we take the regularization parameter lambda to be very small. And we plot the training error and the test error versus the number of parameter. So we can see that the left-hand side, in this curve, the training error goes to 0 when the number of parameter equals number of data, and then stay at 0. And the test error blow up here and then goes down. And the infimum of the test error is achieved at infinity. So in this figure, it displays all the features of the double descent curve. And usually, when people train neural network, they use SGD, and they cannot find exactly the exact minimum. So that means usually, early stopping has some correspondence with regularization. So if we add a small regularization, then the test error will display this shape, and the singularity becomes a mild bound. And then we can plot the test error from different angles. So in these two curves, in these two figures, we plot the test error versus the number of parameter, but these different curves correspond to different strengths of regularization. So if you look at the black dotted line, this is the original double descent curve. If we add a lot amount of regularization for this yellow curve, this is the trivial test error, where you have infinite regularization, so the test error is a trivial one. And in the middle of these two regimes, you have a continuous bunch of curves, and in these shapes.
Can you remind what lowercase n and uppercase n?
Lowercase n is the number of data. Uppercase n is the number of parameters. And if you look, so for the observation is that for any fixed lambda, the minimum prediction error is always achieved at number of parameter is infinity. And the other observation is that if we look at the lower envelope of these curves, so if we look at this curve, and this curve is monotonically decreasing with respect to the number when the number of parameter becomes larger and larger. So that means if when the number of parameter is approximately the number of data, you would like to add a little bit regularization. And as long as you add regularization, then the test error will be monotonically decreasing. The more features, the better. And in these two curves, we plot the test error versus the strength of regularization. So it's a different plot. And this lambda is the regularization parameter. When it's very small, if you look at this black curve, this is the number of this is when the number of parameter goes to infinity. And this black curve, when the signal to noise ratio is high, the minimum of the test error appears when the regularization parameter equals 0. That means if you don't add any regularization, this gives you the best test performance. But when the signal to noise ratio is high, then you would like to add some regularization to get the best performance. Okay, so this is our argument for the tangent kernel theory. So here I have some argument to connect the mean field theory and the tangent kernel theory. Basically, we go back to the two layers neural networks, and the prediction function is simply the average of the neurons, but here we add additional parameter alpha. So this alpha will index the speed of change. It's a scaling parameter. It will index the speed of change of the empirical distribution of the neurons. And the role of this alpha will become clear later. We consider the risk function, which is the standard square loss. And we consider the gradient flow of the parameter theta j. Then, using the mean field theory, we can write down the partial differential equation that corresponds to the change of the empirical distribution of these neurons. And if we define the function ut to be the difference between the prediction function, between the target function and our prediction function at time t, then we can write down the dynamics of this residue function, which follows dynamics associated with a kernel h. And this h, if you look at it, is similar to the neurotangent kernel. But the difference here is that this h will depend on the empirical distribution of the neurons at time t. So the h will change along with time. If you couple these two equations together, you will see that the first equation describes the motions of empirical distribution of the neurons. And the second equation encodes the decay of the training error. And you will see that the decay of the training error will depend on the kernel h. The h depends on the empirical distribution, rho t. And rho t will change according to this distributional dynamics. In the mean field limit, the alpha is fixed, and we let capital N, the number of neurons, goes to infinity. So the two equations, they are coupled. They cannot be decoupled. And in the kernel limit, we take this alpha. So people take this alpha to be of order square root of n. And they take this alpha, and the capital N goes to infinity together. In that case, we can see that because here is a 1 over alpha term, in that limit, the distribution, the empirical distribution of the neuron will hardly change. And then the second equation becomes self-contained because the only place the second equation depends on the empirical distribution of the weights is through this kernel. And if this empirical distribution doesn't change, then the kernel doesn't change. And this kernel, if this kernel doesn't change, this gives you the neurotangent kernel. And you can show that through this equation, the empirical distribution, the training error will converge to 0 linearly. So the intuition in the tangent kernel limit is that the kernel will not change. And then the residual dynamics becomes self-contained. The empirical risk will converge to 0. So let me summarize the mean field theory and the tangent kernel theory. So the mean field theory describes the motions of the neurons as a distribution. The benefit of the mean field theory is that it captures the nonlinear behavior of neural networks that potentially give you better generalization. And now people believe that the mean field regime is what actually happened in practice. Definitely, there are limitations of the mean field theory. It's hard to show the convergence of the partial differential equation. In general, this PDE is a nonlinear partial differential equation, and it will stuck at some bad local minimizer. In general, it's very hard to prove the convergence of this PDE to the global minimizer of the training error. And there are some difficulty to generalize this mean field perspective to multi-layer networks, but this is an ongoing research. Mm-hmm.
In general, I think deep networks, they do not converge to the global minimum, so why would you like to prove that if it's not happening directly?
So at least you want to understand in which case you can converge, right? There are some cases it converges, and some cases it doesn't. So perhaps one wants to understand under some general condition to show that it can converge. Then it gives you a guidance in practice to use this kind of perhaps training algorithm or scenario. Mm-hmm. And then the benefit of the tangent kernel theory is that it gives approval convergence results for even multi-layer neural networks. And it exhibits many similar behavior of fully trained neural networks, basically this double descent phenomena. And this tangent kernel theory, although I didn't discuss in this talk, it's very easy to use in many scenarios. You can linearize ResNet convolutional neural network and even graph neural network and recurrent neural network. You can linearize all these architectures, get a kernel, and prove something, or empirically use this kernel to see if it works. And there are definitely limitations of this tangent kernel theory. So the intuition behind this tangent kernel theory is that the weights, the empirical distribution of the weights are fixed and doesn't change. So this is not the case in practice. And the generalization of this tangent kernel theory is the generalization of the kernel methods, and it's definitely not as good as the generalization of fully trained neural network. And the final comment is that if you say the success of neural network is simply because the success of linear regression, then people will not feel happy. Okay, so these are my summaries for this mean field theory and tangent kernel theory, and thanks for the audiences. Yes.
So for the mean field theory, like what goes wrong with generalizing to multi-layers?
So if you want to generalize to multi-layers, you want to define some empirical distribution, right? So if you have just 2 layers in your network, then the empirical distribution can be defined naturally. But as long as you have a 3 layers network, then the empirical distribution cannot be defined naturally. One way to define it is to say you have a distribution of distribution, but this object is not cannot be treated very easily using mathematics. It cannot be treated rigorously.
Why not? Why can't you just take forwards of distributions?
You can deal with distribution of distribution, but it's mathematically hard. Yeah.
So Brian asked, what kind of foreseeable challenges stopped you from extending your analysis from 2-layer neural networks to those with more layers? You took the number of parameters n to infinity in your analysis. Why didn't you do the same for the number of neural network layers?
Yeah, I guess just now he asked this question. It's because you need to deal with distribution of distribution, so it's mathematically hard.
Another question is, what is the intuition behind the 0 order and higher order terms not being important for deep nets? So why can you assume the network is locally linear? That's what.
So this claim depends on the way you initialize the neural network and the way how you train the neural network. So I guess in the tangent kernel theory, people want to find a way to initialize the neural network such that the 0 order term and the higher order term, they are not important. You can also find another way to initialize the neural network such that perhaps the second order term is important and the other term are negligible. So it depends on your initialization.
But is there some intuition?
Well, it's hard to explain it like off the board.
There's a philosophical question by Anab. In such a modern field where papers are being added on the archive every month, early last year, how do you vet which ones are good and require further work or investigation?
This is a good question. So for me, basically, if a paper that is related to my field, I know what happened in this field, then I can decide easily what is the quality of this paper. If this paper is not related to what I'm working on, then I can ask some friends or discuss with some fellow PhD students and see if this is interesting. If they say they read this paper and they don't feel it's interesting, then I will not bother to read this one. Yeah.
So you rely on the close community.
Yeah, so I mean, at Stanford, many people are interested in this theory of deep learning. And yeah, so it's not just me following all the papers. It's like we are a community, and we can decide which are which are good.
This one. Can the mean field perspective suggest strategies for initialization that will lead to faster convergence, similar to the work by Andrew Sachs? Yeah, maybe you have read that paper. Yeah, basically how does the mean field perspective suggest strategies for initialization? Can you give some insights?
This is a hard question. I don't know how can you come up with a way of initialization uses mean field theory. Yeah, frankly, I don't know.
Given the double descent curve phenomenon in neural net model, is it implying that if computational resources allowed, we should try to make the model as complex as possible?
So I don't think we should. Yeah, I mean no. I mean, given the curve, I mean, it seems that if you use more and more parameters, then the generalization error will be smaller and smaller, right? So it seems to suggest from the curve that we should use more and more parameters. But still, there is a trade-off between computational trackability and the accuracy, right? So perhaps one just want to truncate the number of parameters to the scenario where you can afford the computation, and you think that accuracy is good enough.
In the properties of the double descent curve, Rata noticed that there seems to be a very sharp drop in the performance, in the improvement in the performance after the second descent. Is there any intuition why it's so sharp? And do you think that's another phenomenon that should be added to the list of phenomena that you specify? Maybe you can show the plots again.
Okay. So you are saying this?
Here, the empirical ones. Yeah. Yeah, so you can see it's very drastically decreasing after the, yeah. Is there any intuition why it decreases so much in the second?
I don't know. Because this is log scale, right? So.
I think Amirata wants to.
Uh-huh. Mm-hmm. This one. I don't know. You think this is sharp, but actually this is a log scale, and I mean it depends on the scale, right? It depends on the scale of x. Uh-huh. Yeah, I don't know how to formalize this question. I mean, this is not a quantitative statement, right? So it's hard to, because if you rescale the x, you can make it not so sharp. You can if you want to make it not so sharp. You can just rescale the x. For example, here is a log scale, but if you rescale it to the original scale, then it becomes less sharp. So I don't know. This statement is very quantitative. I mean, yes. Yeah, if you regularize, then it will drop. Uh-huh. You have the same effect of what? Yes, okay. So you are asking if you early stop instead of fully train, then the effect will be similar to regularization. Uh-huh.
For the over-parameterization in the linear model case,
Mm-hmm.
so if I just have some d-dimensional examples and I say my output is linear in that plus noise, that was the model override,
Mm-hmm.
what does it mean to be over-parameterized? Is it the only set of variables like d-dimensional?
Oh, okay. So I guess in neural networks, there are 3 parameters: number of data, the dimension of x, and the number of parameter. So if you just look at a naive linear model, then there are only 2 parameters: dimension of x, which is the dimension of beta, and the number of parameter. So they artificially get a new axis, which is, they say the dimension of beta is fixed. So beta star is a k-sparse vector. And the dimension of, but in the fitting model, when you want to fit this model, the beta, you can take it to be a very large dimension. Yeah, so they call it misspecified model or sparse model, so that there are 3 parameters. Then you can adjust them and play with them.